Okay, good morning, everybody, and welcome back. I hope you had a good long weekend. And we're going to continue our discussion today about evolution of the vertebrates. Again, I just want to emphasize that I am absolutely having to just skim through the information to try and give you a skeleton to build on. This is actually a complex topic, and I urge you to please go and read this chapter to flesh it out for yourselves. And as you do so, a lot of the stuff will actually become clearer. But unfortunately, due to constraints of time, I simply have to skip along through it. So there's just a couple of things I want to emphasize from our previous discussions. I just want to come back all the way back here to this phylogenetic tree here, because we are going to spend a little bit of time talking about the fishes, and we're going to see that there are actually two groups that belong in a single clade, and these are this group, the chondrichthyes, which are the sharks, and then this group here, the osteichthyes, and we've already said that in actual fact is the group to which we belong. There's just one thing I want to make clear. You may still see when you read in other sources that we used to think that the chondrichthyes, the sharks, were a primitive group, and that the osteichthyes arose in a way from the chondrichthyes, or at least that what we see in the sharks, which is this cartilaginous skeleton, is the primitive form. In fact, it turns out that that is not the case. That cartilaginous skeleton is not an ancestral trait. It is a derived trait. It is specific to this group. And they are not in any way ancestral to the bony fishes, of which we are one. So just want to make that clear, because I saw that there's a question in your assignment that asks that very thing. Okay, so here we are, and believe it or not, yes, we belong to this incredible group, huge group called the osteichthyes. And these are the ray-finned and lobe-finned fishes. So we should really call them the ray-finned fishes and the lobe-finned animals, because that is more correctly descriptive. And it is in this group, this vast clade, that most of the living vertebrates belong. And we have to look closely at our fishy relatives, at the things that we recognize as being true fish. But it has to be said that this word fish is not actually scientifically correct. And we need to clarify that there are various groups who belong to that vague designation of the fishes. So this group to which we belong, the osteichthyans, are called the ray-finned fishes and lobe-finned fishes, or lobe-finned animals. And they all of them possess a bony, mineralized skeleton, unlike the sharks, the chondrichthyans, where the skeleton is largely made up of very strong cartilage. In this group, the osteichthyes, instead, the endoskeleton is heavily invested with usually calcium phosphate as the major mineral salt to make up true bone. So the aquatic osteichthyans actually is the group which we informally will refer to as the fishes, and we'll see that there are actually three kind of distinct groups there. So here is a generic fish, a trout, for you. Let's just have a little bit of revision about what makes this, for example, what puts this into its various groups. First of all, it is a chordate. So the reason it is put into the chordates, first of all, if we followed its embryology, we would see that it had a notochord. Here's the dorsal surface, the dorsal side here. There would be a note somewhere in the embryology. There's a notochord, a stiff cartilaginous rod. In the vertebrates, that stiff cartilaginous rod does not persist into the adult form. Instead, it forms part of the vertebrae. And it actually forms the centrum. The biggest articulation surface of each vertebra is derived from the notochord. Second, there is a dorsal hollow nerve cord. That is the spinal cord for most vertebrates, and an extensive nervous system that radiates out from that. But that spinal cord runs here dorsally, and if we were to dissect it, we'd find it was a hollow tube. What are the other chordate characteristics? Well, if you've ever skinned a fish, you'll recognize that the muscles run like this in distinct segments, so that they have segmented muscles. Here is the anus down here, and here's the tail. They have a post-anal tail. But we want our attention now to come to here, to the head region, because there's lots of interesting things going to happen up here at the head region. First of all, the fishes are jawed. They are gnathostomes. They're members of the group, the Gnathostomia. That is because they have true jaws. Those jaws in evolutionary history were derived from supports, gill arch supports. What's the other characteristic of the chordates? They have their pharynx has pharyngeal gill slits, has pharyngeal slits in it. Indeed, when we dissect the fish, have a look here. Here is the mouth. This is the pharynx. It's leading to the esophagus and then to the stomach. But look at it here, and you'll see that, in fact, it is perforated with these slits. In the true fishes, these are the gills. These form the gills. Those are gill slits, sorry. And on the sides of those slits are the gills with which the fish respires. In the true fish, the gills are covered with a single cover here called the operculum. If you go back to the sharks, and I don't have a very good picture. If you have get a bigger picture of the sharks, you'll see their gill slits open to the outside directly. They're not covered with an operculum the way they are in the fishes, in the bony fishes. So here are the gills perforating the pharynx. Now, the other thing which is really fascinating about the osteichthyes, the bony fishes, is this. Have a look here. Here's the pharynx coming down to the stomach, but look here. Off the pharynx, as a separate organ, there is this organ here, which is a swim bladder. Now, we need to keep a close eye on that. This is a very important anatomical feature, and it's a derived feature for the fishes. The swim bladder is used primarily to regulate buoyancy in the water. It can be inflated and deflated to assist the fish in maintaining position in the water column. But look at its structure. It has, in this case, it has a tube which runs to the pharynx. In many of the bony fishes, a good example is a simple goldfish or carp. That they can actually gulp air and fill the swim bladder. And you'll actually see them stand at the side of a pond on a hot day, especially. You will see goldfish coming up to the surface to gulp air, and they're filling their swim bladders. This is very interesting. Remember how evolution works. Evolution works on existing features. It modifies existing existing features are modified in the process of by the process of natural selection. We need to keep a close eye on the swim bladder because it has tremendous potential. It has tremendous evolutionary potential. And to point you in the right direction, just think about our own anatomy. What do we have? We have a mouth with jaws. We have a pharynx. In the embryo, in our embryology, his embryological history, our pharynx is perforated by gill slits. They don't persist into the adult. Follow our pharynx down, and what happens? The pharynx divides in us. It divides to go off to lungs. There are tubes which go off to the lungs, right? And then there's a tube which leads down to the stomach, the esophagus. We can see, if we look at our anatomy carefully, we can see it's reflected here in the fish's anatomy. So we're going to watch this very carefully, indeed. So the rest of the fish, it has a pretty standard vertebrate anatomy, stomach, liver. They do have kidneys, etc., etc., etc. There are a couple of features, though, which are peculiar to the fish. And one of them is this. This here, the lateral line, is a very, very specialized sensory apparatus. And it can pick up information about the chemistry of the water, but also about pressure. And it is one of the main ways that the fish knows where it is in the water column. So, other than that, what we have to keep our eyes on when we talk about vertebrate anatomy is, first of all, the swim bladder, but second of all, the fins. And in the bony fish, there's a pair here of fins called the pectoral fins. And then there's another pair behind here called the pelvic fins. There's one pair there and one pair there. Wave your arms, wave your legs, and say hello to your fins. Because this is a reflection, a pair there and a pair there. There are 4 limbs. Tetra. Tetra is 4. And we're going to start to hear that word tetra importantly, but here are its origins, here in the fishes. Okay. Is there anything else I need to tell you for the moment about the fish? Now, this group of fish are called the ray-finned fishes. And that is because their fins have a particular structure. And that is that if we looked at the base here, we'd find that if they are there at all, there are many, many little small bones down here. And then many, many fine bones, very flexible, supporting a membranous fin. And the fins, their basic structure is for swimming, obviously, and for maintaining position in the water. But if we look through all of the bony fishes, we find there's huge diversity, and the fins are often modified, highly modified, for different purposes depending on the environment of the fish itself. Okay, so those the bony fish, they're called the Actinopterygii. And the Actinopterygii are the fish with those ray-like fins. Let's just have a look at the phylogeny, and let's have a look at the characters which actually apply to the different groups. Remember, this whole group here, this whole clade, is called the Osteichthyes. What is the overwhelming feature for, what is the feature which the ancestor to this group showed? Well, there were a couple, but the most important one is this, that it possessed a lung or something like a lung, a swim bladder, for example. All of the members of the Osteichthyes, all of them, show some trace of that. I will tell you that in some fish, the swim bladder is secondarily lost. But if you look at the embryology of the fish, you will always find some trace of the swim bladder. That is a derived character for the whole group, all of them, all of us. We share that. If we share little else with the fishes, we share the development of the lung. And now we go have a look at some of the other groups. First of all, there are two fishy groups. And that word fish is not a particularly good one. In our mind, it conjures up a certain picture, but in scientific terms, it's a very loose term. Here are those ray fin fish, the Actinopterygii that we've talked about. But here are another two groups, and these are called the Actinistia and the Dipnoi. Actinistia are these here, Dipnoi here. These are lobe-finned fishes. Now, for this particular clade, look here. Here's a whole clade here. They share a common ancestor, and the feature there that we're looking at is the presence of a lobe fin or something that is derived from the lobe fin. That appears in all of these groups. It appears in both of these fish groups, and it appears in the amphibia, it appears in the reptiles, and it appears in the mammals. All of these groups, we have lobe fins, or we have derivatives of lobe fins. So we've got to look then very carefully at these, because it's through, and we share ancestry with both of these groups, the Actinistia and the Dipnoi. But there are features of those groups which are tremendously important when we want to talk about the evolution of the vertebrates from this basic fish form to the later tetrapod form. Tetra, four, pod, limb. So it's four-limbed. We've got to try and find our way from these groups through to these groups here. And our way forward in thinking about that story is twofold. The first thing that we're going to look at is the evolution of that swim bladder into a true lung. The second thing we're going to follow is the development of the lobe fins that lead to the formation of these four limbs that we all display. Okay, so I apologize. I think that this diagram is missing from your notes, but I'll put this back up for you so that you see the same diagrams that I have here. So we're going to talk about these two groups of lobe-finned fishes. There are two of them, and they're this here and these here. These here are also called, our modern day equivalent is the coelacanth. These here are the lung fishes. We'll hear more about them in a minute. Excuse me. Okay, so the lobe-finned fishes, that was called the Sarcopterygii. These are a very, very ancient group, and they originated in the Silurian hundreds of millions of years ago. And their one distinguishing feature, excuse me, the major distinguishing feature is this. Here, this is the structure of the ray fin fish fin. And you'll see it has, there's usually it's attached to the body somehow, to bone. But in what we might think of as being the wrist, there are hundreds of little tiny bones here. And then if from those, we get the rays, these long, flexible bones that support this membranous fin. So this is obviously particularly designed for swimming and for maneuvering in the water. But the lobe-fin fishes took a different path. And in the lobe-fin fishes, when we look at the structure of the fin, it's quite different. Look here, it all works on one bone attached to the skeleton. So there's just one bone here. And then there are a set of, the number does vary a little bit, but this is the basic plan. Here's a pair of bones, then there's a whole lot, and then there's more here. Okay, looking at that, touch this here. What is that? That is your humerus. And that is what this is in the lobe-finned fishes. That is, it is called the humerus in the lobe-finned fishes. Look here, these two bones, feel here on your arm. Swing your arm around like this and you can feel them rolling around underneath you. That's the radius and the ulna. There they are there in the lobe-finned fishes. Now these all here are the bones which are going to eventually, we'll be able to follow them through evolutionary history to form, that they go to form the digits and the carpals and metacarpals, everything that makes up the end of the limb, the hand or the foot are here. The potential is here in these lobe-finned fishes. That's what you must think about. When you see this kind of structure, you must see the evolutionary potential that arose. Now these organisms, let me see, they are very ancient. We see them widely in the fossil record. And here they are here. Here's the lobe fin here. There's the anal fins there. I mean, sorry, the pelvic fins there. Pectoral fins there. They work completely differently to the ray fin. They can actually be used independently. They can move one, I'm trying to get my hands, one and the other, one and the other. And when we look at, we actually have modern versions of these fish. And there are three lineages. These are the coelacanths, the lungfishes, and then us, everything else, the tetrapods. So the coelacanths are very interesting because they're very well represented in the fossil record as a very ancient group that lasted for a very long time, but then they dwindled. They didn't become extinct, however. We discovered in the 20th century, in the 1950s, a living coelacanth was found, was caught actually. They discovered it in a fish market and then mounted huge scientific expeditions. And we've actually now got several examples of coelacanths. And here they are here. Here you can see there, one of the fins. And here is the other one here. So there's a pair there and a pair there. This is an anal fin, it's a single fin. Here's the pectoral on the other side. Here is the pelvic fin. When you watch coelacanths, they followed them alive. They are a bottom-dwelling fish. And they actually maneuver their way across the ocean floor by effectively walking with these lobe fins. That appears to have been the major advantage of having this lobe fin. We believe that, in fact, that most of the lobe-finned fishes lived in relatively shallow water. Many of them in estuaries and places like that. And that this lobe fin was a huge advantage because it enabled them to actually walk where swimming was not very easy. So they could effectively walk through the water, walk along the substrate. And when we watch living coelacanths, that is exactly what they do on the ocean floor. They walk in a very distinctive walking mechanism. So immediately the bell should start ringing, because this is a feature which can precede true walking. Okay, this lying there is the potential for these organisms to actually be able to maneuver a little bit on land, which is ultimately what begins to happen. Now, the allied group for the coelacanths and those kinds those lobe fin fishes are these, and they are the lung fishes. And at first glance, you'd wonder why they are allied to the coelacanths. The reason is, have a look here. This is an Australian lungfish, and you can see here that they have lobe fins. In many of the other living lungfishes, the fins are highly modified. So it's difficult to see, but if we look carefully, if you dissect them, you'll find the same structures. You'll find a humerus, radius, ulna, etc. This is an African lungfish here. This is a South American lungfish here. And this here is an ancient lungfish, this in the fossil record. But we can see the link here between the coelacanths and the lungfishes. The living lungfishes are highly modified because they live in very specialized habitats. Most of the lungfishes live in rivers and ponds that periodically dry up. And this is indeed probably what the ancient lungfish did as well. So they had a tremendous problem. First of all, if you watch the living lungfish, African lungfishes, they very often live in these ponds which dry up. Actually, as winter approaches in Africa, the summer is the rainy season and all the water sources are full. As winter approaches, they begin to dry up. As they dry up, two things happen. The lungfishes that live there, and they're often very numerous, begin to compete with one another. And the water becomes choked with animals. They use up all the oxygen in the water, and besides which, the water is hot. The water is warm, so it doesn't carry much oxygen. And you will see the lungfishes coming up to the surface and actively breathing. And here's what's so fascinating about the lungfish. That swim bladder that we saw earlier, that now forms a true lung. It begins to act, looks like a swim bladder, but it begins to act as a true lung. And if you look at the anatomy of the lungfish, the really important thing is that they can switch their blood circulation. Under normal circumstances, they have gills, just like the other fish. The circulation predominantly goes through the gills for oxygenation. But when they're oxygen starved and they begin to breathe air, they shut down the circulation to the gills, and instead they start to use the lungs. They start to oxygenate blood through the lungs more. They can also, by the way, get oxygen through the skin, but you can see how the lung now begins to function as a true lung.
So, Professor, I have a quick question. Can they survive completely without the water?
Yes. Yes, I'm going to show you now. In actual fact, despite the fact that these look so flimsy, here's one here. I think this is an African one, rather. Despite the fact that they look so flimsy, these fins are actually quite strong. And these fish can migrate across land, and they can migrate for a long distance. They don't do it in a true walking fashion. They do kind of slither along, pulling themselves with the fins. But they will try and get from one pond to another if there are ponds in the area. But then as winter approaches and the water dries up entirely, this is what they do. They go and they form a cocoon here. They make this is a cocoon made of mud and mucus. And they go into a state of like suspended animation, almost like hibernation, excepting that they are breathing air. And so one of the things is that you can do in Africa, you can dig into the bottom of these ponds and you can pull up these cocoons. And this is what you'll see outside people's houses. You'll see these cocoons all stacked up, and you can keep them. They live quite happily in the air. When they do need to breathe, they don't breathe irregularly, but when they do need to breathe, they can breathe through the lung. And if you keep them, and whenever you want fish, you crack one of them open and you kill the fish inside and you eat it. So it has forming this cocoon is certainly a big advantage for the fish to be able to survive drought. But of course, human beings, we always manage to find some way to make it useful for ourselves. But yes, they are fascinating organisms, and indeed they can live for considerable amount of time on land, and they can survive by breathing air in these cocoons as well. Hearing that story, you begin to realize what it might have been like all those hundreds of millions of years ago, when organisms were in shallow water and they were competing with one another. And up on land, there were no vertebrates. The land was open. There were animals there. There were organisms. There were plants, and there were arthropods and things up on the land, but no vertebrates. It was an open niche, and organisms like the lungfish ancestors and things like this that could come up onto land temporarily began to have a huge advantage. And we believe that that is the way in which, in actual fact, organisms with all of the preparatory mechanisms for these four limbs, with an ability to breathe air, even if it was not that efficient, if they could get up onto land or up into the shallows, even temporarily, it would be a huge advantage because it would take them away from competition. It would open up new ecological niches for them. And we believe that that is exactly what happened. You don't need to pay particular attention to this. I just want to emphasize that this is the two most significant events in the evolution of the vertebrates, was first of all, this transformation that we see as the basis of the basic form of the lobe fin is modified to ultimately form the fully functional tetrapod limb. That's the one. The other major thing is the development of the lung and the ability of the lung to breathe air on land. So the group that we're going to pay our attention to now are the tetrapods. We are tetrapods, obviously. And the tetrapods have these specific adaptations. The first is the name. Tetrapod, it tells you 4 limbs and feet and hands, well, hands in our case, but most cases feet with digits. And for the most part, that they are pentamerous. You have 5 digits on each foot. Here's another characteristic. It may sound very, very obscure or rather strange, but all tetrapods have a neck, which other organisms do not. Think about a fish, okay? The fish, even the lungfish, those things, there is no neck. That is a disadvantage because it means that the eyes, the sensory apparatus, cannot be turned independently the way that we can. As soon as you acquire a neck, the body can stay still and you can direct the sensory apparatus all around in a much more advantageous way. The next thing is that all tetrapods have this feature that they have a fusion of the pelvic girdle to the vertebra, to the backbone. That is not the case even in the lobe fin fishes. Why? Why is this of particular importance? The answer is that it gives strength to the whole body, and it allows a body to resist gravity. We need to realize the huge difference between an aquatic organism, which is supported by the medium that it lives in. The water makes it effectively weightless. When you take that body, you put it up onto land, suddenly that body is subject to the forces of gravity. And if we want to move up on land, you have to resist the force of gravity. You need a strong skeleton. And this is one of the features that allowed organisms to begin to move when they were on land. Don't think of it that this fusion developed after they came up onto land. This is, as always with these evolutionary processes, this is a feature which is present in the ancestral aquatic form, but it allowed development of organisms that could move up onto land. The next thing about coming up onto land is it's hopeless to have gills. In the fishes, they have elaborate gills, which work really well because they are supported by the water. They're effectively weightless. Take a fine feathered gill like that, and move it into the air, and what happens? It collapses, and it can no longer function as a gill. So the truly terrestrial organisms lost the gills. They had to develop some other system. I will say that there are some specialized vertebrates which are aquatic, which do maintain a gill. So some amphibians, for example, but they are an exception. It's a specialization in their case. The next one is one that you might not immediately think of. And that is that tetrapods actually all have an ear of some sort. They have some way of hearing airborne sound, and that stands to reason. Move up onto land, you're no longer depending on water for the transmission of sound. Water transmits sound extremely well, and sound can be picked up. For example, in the sharks and in the fishes, sound can be picked up all along the body, along that lateral line, for example. But when you come up onto land, you need a specialized hearing apparatus, because in fact, sound is transmitted rather poorly through air. So you need a specialized ear for detecting airborne sound. Okay, so we need to be thinking way back about those lobe-fin fishes and those sorts of things, occasionally coming up on land. Maybe they have to move from one place to another or whatever. But when they do leave the water, they are entering an environment which might offer particular advantages to them. And we believe that in evolution, there were intermediary forms that gradually more and more exploited the land environment more and more. Here's an organism. It's called Tiktaalik, and it is very difficult. When we're going to look at this organism, it's very difficult to tell whether this is a very advanced lobe-finned fish or whether it is a true tetrapod, and in fact whether it is this basal group of tetrapods called the amphibians. We look at this organism, Tiktaalik, and we see a mixture of all of these different features. First of all, it has a neck. Here it is here. It's quite a large organism. And here it has a neck here. It has this skull that looks rather reptilian, rather crocodilian in a way, although it's not related to them at all. However, when we look at the skin, the skin of this organism was fossilized quite well. And in actual fact, it has scales. Now, no true tetrapod has scales. Only the fish have scales. So this is a fish character. The second thing is, it actually definitely had fins. It didn't have true limbs. It had fins, but they were here. You can see here. Have a look at the the skeleton of the fin, and it is just so advanced. It looks really like a primitive limb, like a primitive arm. But around it in the fossil, we can see that it actually functioned as a fin. So it was definitely aquatic. We believe also that it probably could respire to a certain extent through the skin, but in addition, we believe that it possessed lungs. It had gills, it definitely had gills, but we believe that it also had lungs as well. So this organism, Tiktaalik, it looks like this is definitely an aquatic organism, but it has all of the potential for spending a certain amount of time outside the water. And maybe it spent a lot of time in the very shallow water, venturing up the mud banks, that sort of thing. It was definitely predatory. So it was hunting. There was plenty of stuff to hunt both in the water and on land. There were arthropods and things up on land it could have been hunting. So this is an organism, we believe, one of these ancestral organisms. Something like this would have been an ancestral to the tetrapods, spending some time in the water, some time up on land. And this, not long after Tiktaalik, in the fossil record, we begin to see this particular group, which are called the amphibians. And the amphibians are a group which is still very, very much present on the planet, but also a very, very ancient group. And we know them, the frogs, toads. They are in the order Aenura here. This order here is called the Urodela, and they are the newts and the salamanders. And then there's another group which we won't pay attention to called the caecilians. Believe it or not, this is in actual fact a vertebrate. It's not an earthworm. It's in this peculiar group of amphibians called the apoda, the caecilians. We won't talk about them. So these, let's have a look at both of these. First of all, they very distinctly have a neck. They have very, very good hearing. In fact, they communicate. The Aenura, especially, communicate through producing airborne sound. They hear very, very well. They do not have scales, unlike Tiktaalik. They do not have scales. Instead, they have a moist skin, and they can actually respire through the skin. But all of the amphibians possess a very well-developed lung as well. So they are adapted for life on land. The different groups spend different amounts of time on land. For example, the Urodela, the newts and salamanders, spend more time in the water. They survive perfectly well on land for a time, but most of them spend most of their time in water. The Aenura, the frogs, toads, spend most of their adult life up on land. They are somewhat dependent usually on having a relatively moist environment, or else special adaptations to dry environments. When they, for example, in very dry environments, some of them begin to, they go into a state of suspended animation called aestivation. But when they're up and moving around, they are somewhat dependent on a humid, damp environment, because otherwise the skin dries out very rapidly. Obviously, here is the major development that distinguishes them from something like Tiktaalik. That is that they have very well developed limbs, and the limbs are able to support the body against the force of gravity, and they can locomote with the limbs. They locomote by various means. The first way is by actually walking. The second way in the Aenura is by hopping, but it's just as valid a form of locomotion as any other. So this group, the amphibians, that means amphibian means partly land, partly water. They spend part of the time on land, part of the time on water. They are very strongly, they can venture very far on land, but they are absolutely tied to an aquatic environment by their reproduction, because their reproduction, their eggs require the presence of water for two reasons. First of all, fertilization takes place in water. Eggs and sperm are released free into the water, and fertilization is external. The second thing is that they spend quite a long time in a developmental phase, and that is absolutely tied to water. The larvae of the adult are aquatic, are fully aquatic. So they are very strongly tied to water, despite the fact that they may be well adapted, the adult may be well adapted to living on land. So this, when we look at the amphibians, we realize that what we're looking at is very strong adaptations for being up on land. You'll realize, for example, that all the frogs, toads are in fact predatory. They feed largely on arthropods up on land. They spend most of their adult life up on land, doing whatever they do. They may be very specialized for particular habitats, but all of them in one way or another are tied to water still and are partially aquatic because they are required to reproduce in water. Now there's one or two.
Wait, real fast,
yes,
Professor.
Go.
So that will make frogs tetrapods because they don't have gills, they have neck, they have the little limbs that they can walk on. That makes them tetrapods? Okay.
Yes, yeah, they are fully tetrapod. They're fully tetrapod. They have 4 well-developed limbs. They have a neck. They have ears to hear and a well-developed lung as well. So you are correct. And we look at the amphibia now, and we recognize them as being our most primitive tetrapod group, existing tetrapod group. But looking back at the fossil record, for example, you can see how strongly they are tied to those kind of lobe-finned groups as well. It's not a big jump from those, so to speak, from the lobe fins to primitive amphibians. So in terms of moving up onto land, the colonization of land is one of the driving forces for vertebrate evolution. And we need to think really carefully about what it means to come up onto land. We've already heard you can't have gills if you up on land because the gills collapse. You've got to have limbs which can resist the force of gravity. You've got to have some way of respiring. Now, in the amphibians, they can respire through the skin, but that limits them somewhat. It's difficult for them to move into really dry habitats because they have this moist skin. But the huge disadvantage, the thing which prevents the amphibians from being truly terrestrial, is the fact that their eggs are not adapted to being laid on land. If you take most amphibian eggs, take them, put them up in the open air, they dry out really quickly. Besides that, the amphibians, most of them have a larval form which requires the presence of water. In the amphibia, the fertilization is external and it takes place in the water. So these are all things that tie the amphibia to the water, but they also a limitation on the amphibian group. And the next group of vertebrates that we need to look at are a group that became freed from that dependence on water. And these are a group called the amniotes. And the amniotes are a group of tetrapods which reproduce away from water. And the most important thing about them is that they developed a specialized egg. It's an egg which could be laid on land and survive and develop on land away from the water. And that meant that these groups, the amniote groups, could move well away from water and up onto the land, as long as they had a source of water for drinking, etc., obviously. But they were no longer dependent on water for their reproduction. So the development of this specialized terrestrial egg was the next huge advance in the vertebrate evolution. So what do we have? We had all of the Osteichthyes. They have lungs or lung derivatives. This lobe fin clade, they all have this lobe fin or development, an elaboration of the lobe fin. This whole group here, these here are the tetrapods, and they are the amphibia and everything else. They have these 4 limbs, and they have a foot on each limb with digits, and the digits usually 5. However, the amphibia were limited because they were tied to water for reproduction. The next groups here, the reptiles and then the mammals. These groups here all have this distinguishing feature, that they are able to lay an amniotic egg. And an amniotic egg is an egg which is specially adapted to develop on land away from water. So the whole development of the larval form takes place inside the egg, not in an aquatic environment. Well, it is in an aquatic environment. I'll point that out. We still develop in an aquatic environment. It's just that our aquatic environment is now enclosed. And we don't have to be in water itself. Our aquatic environment takes place in this special circumstance, the egg, that's the amniotic egg. So this is the typical egg. This is a hen's egg. I would point out that the hen's egg has this hard calcium carbonate impregnated outer shell. That is not often the case in actual fact. Most organisms that lay an amniotic egg, this is the outer shell is a thick membrane, a very thick, tough membrane. It is specially adapted. It has special characteristics in that it allows the percolation of oxygen through it, and it allows percolation of carbon dioxide out of it. So the organism can actually effectively breathe through the shell, but it restricts the evaporation of water. So the egg does not dry out. The shell and the membranes are specially designed to conserve water on the inside through the whole development of the organism. I'm not going to go through all of the different membranes. I just want to show you that that word amniotic refers to this, and this is the amnion. It's a membrane which surrounds the embryo. There it is there. So what the amniotic egg is an elaborate system of membranes, and those membranes surround the embryo. The amniotic egg provides a food source to the embryo. In an independent amniotic egg like this, that is in the form of a yolk. This becomes a little bit more elaborated, as I'll talk in a minute. There are various membranes. Amnion, just remember the amnion are immediately around the embryo because that's what the amniotic egg gets its name from. Then there are other membranes called the allantois and the chorion there. And then there are other membranes that make up the outer shell. of the amniotic egg. An elaborate system, but look what it's doing. It's providing an enclosed environment where the water is conserved. The embryo develops now in an aquatic environment whose chemistry is very carefully regulated. And the loss of water through the shell is very, very restricted, but the embryo can still gain oxygen and breathe out, lose its carbon dioxide. The embryo now is independent of water. And if the embryo is independent of water, then the organism itself is independent of water. This egg can be laid on land far away from water, and it can still develop. Now, the other thing to realize is that we'll see throughout these groups, throughout the amniotes, different ways in which this egg is treated. In many, many, many of them, the egg is simply laid outside and develops. But in others, some of them keep the eggs inside. They keep them, they still have all of the membranes and everything, but they maintain the egg inside the female body. And ultimately, as in us, in a group called the placental mammals, the whole shell structure is lost, and instead these membranes become associated with a specialized organ called the placenta. But we still see the same membranes. We still, even though you can think of it like this, you can think that these membranes here, these ones, this whole structure here, forms the placenta in placental mammals. But we keep all of these membranes. So in us, in humans, in mammals, which have a placenta and keep the embryo inside the uterus, effectively what we have done is we've modified the amniotic egg. The actual basis, the actual root of our placental structure is here. It's in the amniotic egg. And exactly the same membranes and everything that we see in an egg laid by a bird or a reptile or anything else. Is that okay? All right, so I'll just finish off by telling you that this split between the amphibians and the amniots, their last common ancestor was about 350 million years ago. And this development of the amniotic egg allowed them to begin to penetrate far into land, far beyond where any of the amphibians had been able to go. And the other important thing is, driving feature for them was that they were probably predatory. They were probably predatory and had ended up competing tremendously with one another in that narrow band associated with the aquatic environments where the amphibians all lived. So this ability to move onto land away from the water opened up all sorts of ecological niches for them. And that's the story that we're going to follow next. Okay, are there any questions?
No, but the amniots, that's starting like something different from what we were learning in the beginning, right?
Yes, how different from, no, just clarify for me.
Not different, but like kind of like starting a new, not a chapter, but a new topic that we're going to discuss.
Yes.
Okay.
Yes, exactly. We're going to move on now. We're going to move on now to talking about this whole group. Okay, because these are the reptiles. I know it looks very complicated. We're going to have it quite simple. The reptiles here, this whole group here, and then this group here, which is our group, called the synapsids there. So these all developed from the ancestral amniot that laid that kind of terrestrial egg. Okay. All right then, everybody. I'll see you then. What's today's Wednesday? Yes, go ahead.
For the extra credit, are you going to post a submission box or should we email it?
No, just email it to me, please.
Okay, thank you.
Yep. Thank you.
Enjoy the rest of your day, Professor.
You too. You too. Thanks for stopping by.
Professor.